Okay, so this admittedly is going to be a pretty long and gory problem, all right? So you have to be very careful with your algebra on problems like this, all right? And this does represent basically what could be the hardest calorimetry problem. You know, I can do little things with units here and there, not that hard, but solving for one of the temperatures is difficult, okay? Solving for a change in temperature, not so much. Solving for one of the temperatures gets algebraically a little tricky, all right? So where do I start? I always start at the same place. I start with my mathematical representation of conservation of energy. All right, so I have hot lead being placed into a calorimeter containing 100 milliliters of water. All right, so water is going to increase in temperature and lead is going to decrease in temperature, which means Q, the lead is going to have a negative value and the Q of the water is going to have a positive value. Okay, so turn this in mathematically. Negative Q negative, just Q water equals negative Q of the lead. Okay, could also do metal here. That might make my life a little easier. And in fact, I am going to do that. Okay, now this is just straight MCP delta T stuff again. Mass of the water, CP of the water, delta T of the water equals negative mass of the metal, CP of the metal, delta T of the metal. Okay, so this is why it's going to start getting brutal. I'm going to show you how to do this purely algebraically. Sometimes things will cancel out, and it's good to see at this point. Like say, if I use the same mass of metal as water, something would cancel out, and that would be very nice, okay? But I didn't because I wanted to show you the gory, all right? So I'm going to have to do everything here. And the first thing that I'm going to need to do is I'm going to need to expand these. And remember that this is T final minus T initial. And this is T final minus T initial. And the important thing to remember is this is what we're trying to find. It's going to be the same for both. All right? So mass of the water, CP water, T final minus T initial of the water equals negative mass of the metal, CP metal, times T final minus T initial metal. Now, the other thing that's kind of a pain here is you got to keep these T initials straight, which gets just long and drawn out and super ugly. All right, so the next line, I'm going to distribute everything. Mass of the water, CP water, times T final minus mass of the water, CP water, T initial water, equals negative mass of metal, CP metal, T final, and then a negative times a negative is a positive, and I'm going to actually make this a better positive, plus mass of metal, CP metal, T initial metal. All right, now I'm going to get my T finals on one side. Okay, so I'm going to add this whole thing to both sides, and I'm going to get everything else on the other side. So I'm going to move this one. I'm going to add mass of water, CP water, T initial water to both sides. So I get mass of water, CP water, times T final, plus mass of metal, CP metal, T final, equals what are we doing here? Mass of water, CP water, T initial water, plus mass of metal, CP metal, T initial metal. Okay, now, at this point, I can combine like terms here. And I can say that T final is M water, CP water, plus M, well, here, let me just write it out, T final. Mass of water, CP water, plus mass of metal, CP metal, times T final equals all this stuff. Okay, and now I can divide both sides by this mass of metal, CP, mass of water, CP water. Divide both sides by that. Plus mass of metal, CP metal. Both sides. T final would thus equal mass of water, CP water, T initial water, plus mass of metal, CP metal, T initial metal, over mass of water, CP water, plus mass of metal, CP metal. All right, good. Glad you're still coming with me. Now, finally, I am going to plug in numbers. With a problem like this where nothing cancels, it's probably a good idea to start plugging in numbers like higher up here, just to maybe make your algebraic life a little easier. But I think it's important to get to at least this step where everything's out. You can kind of see it. You can see if things are going to cancel out. Yeah. So mass of the water is 100 grams, 100.0 grams. Okay, and this came from the volume of the water, which was 100.00 milliliters. Okay, times CP of water, 4.18 joules over grams degrees Celsius, times the delta T, times T initial water, which is 22 degrees Celsius, plus mass of metal, 25 grams, times the CP of the metal, which is 0.129 joules over grams degrees Celsius, times delta T, which is 95 degrees Celsius, or T initial metal is 95 degrees Celsius, over mass of the water, 100.00 grams water, times 4.18, plus 0.129 joules over grams degrees Celsius, times the mass of the metal, which is 25.0 grams. Okay? And when I do this, I get a whopping 22.6 degrees Celsius. So the temperature of the water increased by 0.6. Okay? So that gives you an idea of why we use water as like what we put things in for calorimetry, because water doesn't change temperature very much, whereas other things do. All right? So again, this was about as long and gory as I can make them. This, where you find the T final, those are awful. Okay, I'll admit those are awful. If I'm going to ask you to do one, I'm probably going to give you a shortcut. Okay, so like something's going to cancel out. So keep your eyes out for that.